Related graphs or transformation of graphs. In this section, we will examine how changes to the equation of a function affect the graph of the function. We will confine our discussion to 4 basic changes. So the first change, y equals f of x plus or minus some value a. The function f of x equals x squared is shown. So focus in on the black curve. So the black curve, the U-shaped graph, is y equals x squared. The function f of x plus 2 represents a translation vertically upwards by 2 units. So focusing in now on the blue curve, so it's the exact same shape, it's just been moved upwards 2 steps. So this is the graph y is equal to x squared plus 2. The function f of x minus 3 represents a translation vertically downwards by 3 units. So focusing in now on the red curve. So it's the exact same shape, it's just been moved down 3 steps. So this is the curve or the graph y is equal to x squared minus 3. So if we have a positive a value, so whatever is added on to the end of the function, if it is positive, it moves the graph in the positive y direction, so it moves it up. And if it's negative, it moves the graph in the negative y direction, so it moves it down. Next, we have y is equal to f bracket x plus or minus a bracket. So if a, some unknown value, is added or subtracted to the x inside the function. So the 3 graphs on the right show that y equals f of x plus 2 represents a translation of the function f of x equals x squared by minus 2 units parallel to the x-axis. So if we focus in on the black curve, that's the original function that we had in the previous example. So that's just y is equal to x squared. And the function y is equal to x plus 2 to be squared is the exact same function. It's just been moved 2 steps to the left. So we started off with the black function and it was moved 2 steps to the left to get the blue function. So it was moved to the left, but it's a positive inside the brackets. So inside the brackets, if it's a positive, so in this case it's positive 2, it's moved to the left. F of x equals x minus 3 to be squared represents a translation of 3 units parallel to the x-axis. So focusing in now on the red curve. So the red curve has been moved to the right. So if we were thinking of the black curve as the original function, y is equal to x squared, then the red curve was moved 3 units to the right, so 3 steps to the right. And this is the function y is equal to x minus 3 to be squared. So there's a minus 3 inside the brackets, so we move it 3 steps to the right. So y is equal to f of x plus a, so a positive value, results in translating the graph parallel to the x-axis by minus a units, so basically to the left. Y equals f of x minus a, so a negative value for a, results in translating the graph parallel to the x-axis by positive a units, so moving it to the right. So if it's positive inside the brackets, we move it to the left. If it's negative inside the brackets, we move it to the right. Y equals minus f of x. The graph of y equals minus f of x is a reflection in the x-axis of the graph y is equal to f of x. So again, we have y equals x squared as our original function, so our U-shaped graph, so that's in black. And we can see that the graph of y is equal minus x squared is just a reflection in the x-axis, so it's just been flipped upside down. So the minimum point, which in this case was 0, 0, is now the maximum point. The graph of y equals f of minus x is a reflection in the y-axis of the graph of y is equal to f of x. Y equals a f of x. So some value of a multiplied by the function, so stuck onto the front of the function. So it's important to note that it's stuck to the function, so there's no plus or minus in between now. The graphs of f of x equals x times x minus 1 times x plus 2, and f of x equals 3x times x minus 1 times x plus 2 are shown. So we have the function f of x equals x times x minus 1 times x plus 2. So that's the red curve. And you can see it looks like a sideways S. So that means it's a cubic function and it's going upwards, and then it turns and it goes downwards, and then it turns and it goes upwards again. So it's positive x cubed. So if we were to multiply out our brackets and simplify, our highest power of x would be 3. But that's not relevant to this particular type of question. We're interested in the shape of the graph and what happens when 3 is multiplied in to the function. So the blue curve is f of x equals 3x times x minus 1 times x plus 2. So the only difference between them is we have a 3 stuck onto the x, whereas down here we just had an x. So multiplying a function by a constant will not change the points where the graph intersects the x-axis, but it does have the effect of stretching the graph up and down. So we can see that the maximum point has been moved upwards. So the maximum point lined up with 2 on the y-axis, and now it's up as far as 6 on the y-axis. So to be honest, this graph is not drawn very accurately. It should line up with 6 on the y-axis if the maximum point was 2. So this is a little bit above 2. We'll say it's 2.2. So this is going to be 6.6, let's say. So it's been multiplied by a factor of 3. So it's been moved upwards by a factor of 3. And then likewise, the minimum point we can see has also been stretched. So it's moved downwards by a factor of 3. The graph of y is equal to f of x is shown. Use separate diagrams to draw a sketch of y is equal to minus f of x, y is equal to f of x plus 2, y is equal to 2 f of x, and y is equal to f of minus x. So again, here we have a cubic function because it's a sidewards s. It's going downwards, then it turns and goes upwards, and then it turns and goes downwards again. So this is a negative cubic function. So the highest power of x would be 3 in our function, and it would be minus x to the power of 3, or minus something x to the power of 3. So I've just moved it over here to the left so I have a bit more space. So our new function we want to draw is y is equal to minus f of x. So this minus will give us a reflection in the x-axis. So it looks like the graph has just been flipped upside down. Important to note these points here. So minus 2, 0 and minus 2, 0 remains the same on both graphs. It was the minimum, it's now the maximum. Another 2 important points. So we have 0, 4 and 0, minus 4. So it cuts the y-axis at 0, 4 in the original function, and now it cuts the y-axis at 0, minus 4 in the new function. 2 more important points on our graphs are 3, 0 and the same on the other graph. So it cuts the x-axis at 3, 0 on both graphs. So that has not changed. And 2 more important points. So we have 1.5, 6 and minus 1.5, 6 on our reflection. So the maximum is now the minimum. So that's why the 1.5 stayed the same, but the 6 becomes minus 6. So next we have y is equal to f of x plus 2. So we want to move 2 steps up. So again, on our left, we have our original function, and it's going to move 2 steps up. So focus in on this point here, minus 2, 0. And notice that in our new graph, the minimum point is minus 2, 2. So the minimum was minus 2, 0. Now it's minus 2, 2. So the y value was moved up, or we had 2 added to it. So the y value was 0 and now it's 2. And notice that the x value has not changed. Let's take 2 more important points. So we have the maximum, which in the original function is 1.5, 6. And now in the new function, it's 1.5, 8. So the x values didn't change, but 6 plus 2 makes 8. So 2 was added to the y value to make 8. Next, we have y is equal to 2f of x. So what we do is we multiply every y value by 2. So if we focus in on the point 0, 4 on our original function and 0, 8 in our new function, y is equal to 2f of x. So our graph did cut the y-axis at 0, 4, and now it does at 0, 8. So it did cut the y-axis at 0, 4, and now it cuts the y-axis at 0, 8. And 4 multiplied by 2 makes 8. So we multiplied the y value by 2. 2 more important points. So the maximum in our original function was 1.5, 6. And the maximum now in our new function is 1.5, 12. So again, nothing happened to the x values, but the y value was multiplied by 2 because we have 2 stuck onto the front of the function. So 6 times 2 makes 12. The minimum point of our graph is important as well. So the minimum point in our original function is -2, 0. And notice that it is still -2, 0 in our new function. And that's because if we focus in on the y value, which is 0, 0 multiplied by 2 gives us 0. So that's why the 0 doesn't change. So that's why both graphs have the same minimum point. So the maximum point did change, but the minimum point did not change. So that's the minimum turning point of our graph did not change. And then we have y is equal to f of minus x. So this time the minus is inside the brackets instead of at the front. So this is a reflection of y is equal to f of x in the y-axis this time. So an important point to look at is 0, 4 on our original function. This is where it cuts the y-axis. And notice that it still cuts the y-axis at 0, 4 in our reflection. So that's important to note, that it cuts the y-axis at the same point. Some other points to have a look at on our curves are -2, 0, the minimum point, the minimum turning point, and 2, 0, the minimum turning point on our reflection. So the minimum was -2, 0, now the minimum's 2, 0. So notice that the x value has changed to the opposite sign, but the y value remains the same. Focusing in now on some more important points. So the maximum of our original function was 1.5, 6, and the maximum turning point of our new function, our reflection, is now -1.5, 6. So notice that the x values changed sign, but the y values remain the same. Now, some more important points are 3, 0 and -3, 0. So it did cut the x-axis at 3, 0, our original function, and now it cuts the x-axis at -3, 0. So we can see it cuts the x-axis at -3, 0 now. So again, the x's have changed to their opposite sign, but the y values remain the same.